My name is Braam. I work with a large group of people on designing computers and software for a new radio telescope that many of you have probably heard of, called the Square Kilometer Array. It will be an instrument on the scale of CERN that does radio astronomy for the world. It will break many new barriers in terms of sensitivity and speed. And there are many new IT-type problems emerging that I think are in the category of revolutionary. I'll tell you a little bit about them. So in this single slide, I'm trying to explain to you very quickly how a radio telescope actually works. On the left, you see the antennas. These are no longer dishes. They're now, the beams are formed with electronics. There is a next electronics component called the signal processor. And what you see there is that it, in the first phase, will take 20 exabytes of data per day. And when the telescope is extended, 200 exabytes. This is actually a relatively simple component to build. A simple single rack of electronics can do this work amazingly. The data, though, needs to be moved over hundreds or thousands of kilometers. Then the real computing starts, where the HPC world comes in. And that part of the story is called imaging. It's not just building images. There are also things like timing pulsars and so on, lots of interesting different measurements, but not very many. There are only about 10 different algorithms that we will solve there. So the ingest in this system is significant. It's about 100 petabytes per day to 10 exabytes per day. The problem is quadratic in the scale. The telescope will go up about a factor 10. The output for 5 years of measurements is 5 years of images is about an exabyte. So we need an archive of that scale. A single image is a 100 terabyte collection of photographs. So we're a little bit ahead of your iPhone camera. Just like with CERN, the data will be processed worldwide, not at the telescope. So this is followed by distribution of these very large images across the world, and then a lot of study how to do data analytics in it. We are not looking for terrorists, but we are looking for aliens. So what is really revolutionary about this particular project? So first of all, the amount of data that goes into the computers here is so massive that it cannot be kept. Yeah, it is. You get one shot at it. You need to process that data in a few hours' time, and then the next data comes in, and there is no space to keep it for much longer. Some of the data is not precious. There will always be broken antennas. Kangaroos will chew on the cables and lots of things. Yeah, so it's a problem where a typical sensor problem where a lot of data will be lost and can be lost. The exabyte output archive is, I think, a pretty big archive, even by 2020 standards. And the worldwide dissemination through a sort of cloud and analytics framework of this is probably not so easy. Yeah? And the lessons learned from CERN are that there are many surprises. But perhaps even more revolutionary is the following. Telescopes get very old. 50 years is a very normal lifetime for a telescope. Every 4 or 5 years, it will be cheaper to replace the hardware than to keep it. And the software is very expensive to construct, and it must be able to adapt to 10 to 20 generations of hardware. So we're making a big effort to build this software not as a monolithic typical HPC application, but with techniques that can both adapt to new algorithms and to new hardware as we go on. So there were two questions that I didn't put in these 3 slides, namely, what is the wider applicability? Well, it is a sensor problem. Yeah, it's not so different maybe from having hundreds of thousands of cameras in a city or so that you need to manage the data from. Secondly, how is this going to market? So science organizations run the risk of building something very much purposeful for their particular problem. We are working as much as we possibly can with vendors, standards, and using COTS technologies, and hoping that in that way we bring this technology out to the world so that others can simply look at how it was done and adapt it. Thank you.
So the telescope is going to last for 50 years. I presume that you want to preserve your data over decades, or are you discarding data?
No, we can only preserve the processed data. The actual input data is discarded every 6 to 12 hours. So the exabyte archive are only the post-processed data. There's no chance to keep the other stuff. It's too much.
Okay, so but the data that you keep, how do you migrate it over generations of storage devices and software changes over time?
That's a good question. You know, FAT is 30 years old, right? The FAT file system. So there is some hope that you could do this. We have also been very, very careful in selecting image standards, the formats of the files in such a way that they have a reasonable chance of longevity.
So this has nothing to do with HPC, but is potentially disruptive. You showed antennas that use beamforming instead of traditional satellite dishes. When am I going to get that at my house instead of a stupid DirecTV thing?
Actually, maybe not so very long. I don't know, but you need quite a lot of these little antennas. They come in pads, these things, so you would need, for a single television, may not pay off. I'm not really an antenna expert, but good try, yeah.
Well, Peter, you certainly have a disruptive problem that needs innovative solutions. Your comparison to the LHC is very appropriate. Not much of the LHC data management technology went anyplace else but LHC, as far as I know. But what seems to be the most interesting part of this that might be useful is your techniques for writing software that could last for 50 years on 50 years worth of new generation hardware. I hope that you can make that available, disseminate those techniques.
Yeah, the experiments, by the way, are all open sourced on GitHub. The project, I think, is called Radio Cortex.
Yeah. Great. Thank you very much, Peter.